I'm Anil Kumar, and in this video, I'll discuss concepts to find limits. And in this playlist, we'll have many examples which you can practice to understand and master the technique of finding limits. We'll actually discuss how to find limits from a graph, how to find limits by direct substitution, by factoring, by rationalization, and by substitution. So I won't take much time here. In short, I will explain you. You can always search for my videos by typing in Anil Kumar limits playlist to get hold of the whole list. From graph, let me sketch one graph here and then we'll talk about limits. Let us say that we have a function whose graph is kind of like this. A hole here, and let's say something kind of like this. It finishes off. Let's say the function is kind of like this, okay, and then like this, okay. So we'll consider a piecewise function so that we can discuss in general how to find limit for a variety of graphs with the help of one. Let's call this point where you see the hole as -1, and this let it be 2, right? This point is 3, and we'll keep that as 4. Okay, those are the y values. And let us see, we want to find limit as x approaches. So kind of important concept is, it is not the value of function at a point, it is the value which you approach. As x approaches -1, let's take this point. For the given function f of x, is it okay? So limit of this function f of x. Well, L is normally lowercase, so we'll make it lowercase. As you approach -1 from left side, you approach a value 2, right? You can see that there is a hole at -1, a discontinuity in the graph. So the value at -1 does not exist. You can see that f of -1 does not exist. It is not defined, right? However, limit exists. If you go from left side, which we normally can write as limit, x approaches -1 from left side for the function. So if you approach from the left side, you are approaching a value 2, so its limit is 2. Limit as you approach -1 from the right side, this plus indicate right sides. For the same function, we are again approaching the value 2. So left side, right side really means that if I am coming from this side, I'll hit this graph and approach this value, which is -2, right? And from the right side, I'm going to be on that part and approach the same value 2. Now, since both these limits are same, right? You can see here that both of them are equal. Both of them are equal, correct? And therefore, we say that the limit of the function exists at -1 and it is equal to 2. Perfect. So that is how you can find the limit from the graph, correct? Now, can you help me find limit when x approaches 0, right? For the same function f of x. Now the answer is does not exist. Do you know the reason why? When you approach from the right side, you approach a value which is 4, and from the left side you are approaching 3. Do you see that? And since 3 and 4 are not equal, the limit does not exist, correct? Because let me clearly write down here why it does not exist. Because the limit as you approach 0 from left side, you are approaching 0 from left side, you approach a value which is 3, correct? Which is not equal to the limit when you approach 0 from the right side. When you approach from right side, the limit of this function is is 4 and they are not equal. Therefore, the limit does not exist at 0, right? So with this example, you have also learned one-side limits, right? So we have also covered one-side limits. You have learned one more important concept, that the limit may exist, but the graph may be discontinuous at this point. So that whole graph is discontinuous. However, the limit exists. Perfect. So these are a few things to remember. Now let's look into direct substitution to find limits. Let's say we have a function which is, let us say 2x minus 1. Now this is a continuous function. If I want to find limit as x approaches 0, the only thing I have to do here is substitute 0 here, right? So as soon as I substitute 0, I get 2 times 0 minus 1, which is minus 1. So the limit exists and it is minus 1. From the graph also, we can find the limit at some point. For example, if I'm trying to find limit, let me say at a point which is, let's say, plus 1. So from the graph, we can say limit x approaches 1 for f of x. We are considering the graph on the right, this function. As you can see, it is constant function after 0, right? And the value is 4. So the limit exists and it is 4. So you can directly read from the graph. Similarly, you could substitute and find in different ways. So that is direct substitution. Let me give you an example here. Limit when x approaches 0 for the function 1 over x. Now if I substitute 0 here, I get 1 over 0. Now that is not defined, it's not a real number, and therefore we can directly get our answer, which is that it does not exist, correct? So by direct substitution, you can also get the value does not exist, just as I've shown you here, right? Now we'll take up examples for factoring. So we'll extend this concept and move on to understand factoring techniques, when to factor. Now let me consider a function, let's say limit x approaches, let's say 2, and we have a function where it is 0 at 2 in the denominator and it is 0 in the numerator also. For example, we have x squared minus 4. Now this function here, if I substitute 2, what I get here is 0 over 0. Now whenever you get 0 over 0, it is called indeterminate. That 0 over 0 also indicates that there is a common factor in numerator and denominator, and the factor is x minus 2, which makes it 0. Perfect. So if I factor and cancel out the common factor, we can actually find the limit, right? So let's do that. So we can do limit x approaches 2. Difference of squares, I could write this as x minus 2 times x plus 2 divided by x minus 2, correct? Now x minus 2 cancels out, and you know we can find the limit, and that is equal to, substituting 2 here, we get 2 plus 2 equals to 4. Perfect. So we get limit of this particular function, which is 4. Let me sketch this in a graph to make you understand the concept. So what we get here is a straight line, which is x plus 2, right? X plus 2. So x plus 2, slope 1, y-intercept of 2, and it is not defined at 2, this function, right? Since denominator is 0, right? So we could have a graph of this kind of like this, where at 2 the function is not defined. Let's say this point here is 2. Is that okay? So at 2 the function is not defined. However, we have a hole whose y value is 4. Do you see that? That's what we really mean. So this factor which cancels out leads to a hole. So that is the given function for us, right? So this is the graph for the function where we factored and found the limit. So with that, we have covered how to find limit from the graph, how to find limit by direct substitution, and how to use factoring concepts to find limit. Now let's move on to rationalization. So if I have a function, let's say g of x is equal to, if we have square root kind of a thing, right? In that case, rationalization is a good option. Let's say we have a function where the limit approaches, x approaches 0, and something which makes denominator 0, we'll put this x and the numerator as x plus 1. So if I write 0, I get 1 minus 1. Perfect. If I substitute 0 here, as you can see, you will get 0 over 0. It's an indeterminate, right? So it is indeterminate. So whenever you get indeterminate, you could apply these techniques, which are factoring, rationalization, and substitution. Rationalization is done when we have square root functions. Remember that. So let's rationalize and find the limit. So we could continue with this and say limit x approaches 0. The function is square root of x plus 1 minus 1 over x. We'll rationalize numerator by multiplying and dividing by its conjugate, which is square root x plus 1, right? And that gives us limit x approaches 0. A square minus b square will be the result. So square of square root will give us x plus 1 here, minus 1 square, which is 1, divided by x times square root of x plus 1, right? Now this is equal to limit x approaches 0. See, in the numerator, 1 minus 1 is 0. You're left with x. And in denominator, we already have this factor x. That resulted into 0, right? And substituting 0. Okay. So we get here square root of x plus 1. Now we can cancel the factor which caused indeterminate. Do you see that? Once we have done so, we can always substitute 0 and find the answer. So we get 1 over 0 here means square root 1 plus square root 1 plus 1, which is half. So limit of this function exists at x equals to 0, and it is half. And this technique is called substitution. Correct? So it's a very important technique which we can always use to find the limit of a function, right? Now we'll take up another example where substitution can be a better option to find. Let's say we have another function, let's call it r of x equals 2. Let me take cube root, right? So cube root functions to rationalize is kind of difficult. Therefore, we use substitution techniques here. We'll say limit, what makes the denominator 0? 8, right? So x approaches 8. So if I substitute 8 here, cube root of 8 is 2. So 2 minus 2 is 0. 8 minus 8 is also 0. So in this case, you could actually rationalize also. You know, a cube minus b cube formula. Let me write down here. A cube minus b cube is equal to a minus b times a square plus ab plus b square. So rationalize a cubic function. We have to multiply and divide by a square plus ab plus b square. Remember that. You could do it, but it's kind of complicated. So we avoid it and we use substitution. So let's do a substitution here by a different variable, right? Substitution by different variable. Okay. Now, let's say u is equals to cube root of x, right? In that case, u cube will be equal to x, correct? So I can replace cube root of x by u and x by u cube. Now what about this limit? As you can see, if x approaches 8, then what is cube root of 8? Cube root of 8 is 2, so u approaches 2. Perfect. So keeping that in mind, we can rewrite our function r of x as limit u approaches 2, right? Instead of x approaching 8, u approaches 2. And cube root of x can be written as u. So we have u minus 2 in the numerator. And u cube for x. So we have u cube. Let me write 8 as 2 cube just to show you that we have difference of cubes. Perfect. Now, I will just expand the denominator so you can see we can cancel out the common factor u minus 2, right? If I expand this using the formula which we have right there, u minus 2 times u square plus ab, which is 2u, plus 2 square, which is 4. Do you see that? Now, we can cancel u minus 2 and get the result. We have limit u approaches 2. And what we have here is 1 over u square plus 2u plus 4. Is it okay? And substituting 2, we get 1 over 4 plus 4 plus 4, which is 1 over 12. So limit of this function exists, and it is 1 over 12. Now let me take a very special case here. We call it absolute function, right? So whenever we have absolute functions, so let's say a of x is equal to, let me write a function, let's say x minus 2 over absolute value of x minus 2, and the limit x approaches 2, right? So if you have this function, absolute function, then you know absolute function is a piecewise function. Whenever absolute function is involved, we have to split it into two different pieces, since you know that absolute value of x minus 2 is equal to x minus 2 for x greater than equal to 2, and is equal to minus of x minus 2 when x is less than 2, right? So when you solve it on both sides of 2, you'll find that it approaches different values, and this limit does not exist. So we get this result as it does not exist. So instead of getting into details here, what I will do is basically sketch this function for you, right? So if I sketch this function in the small space which I'm left with, it will kind of look like this. At 2, we have a discontinuity, right? But if it is greater than 2, then we have positive 1, a constant value. And if it is less than 2, then it is negative 1. Do you see that? This is when x is 2. Perfect. At 2, it is not defined. So when you approach from the left side, you approach the value minus 1, right? From the right side, you approach 1. Do you see that? So what we have is the limit from left. So limit as x approaches 2 from the left side for the function a of x is minus 1, which is not equal to the limit as x approaches 2 from the right side. So this plus, do you see that? Of the function a of x, which actually is plus 1. Now what you see here is that for the given function x minus 2 divided by absolute value of x minus 2, as x approaches 2 from the left side, the limit is minus 1. When you approach from the right side, the limit is plus 1. Now these two values are different, they are not same, and therefore the limit does not exist as x approaches 2 for a of x. Correct? Now that brings us to the end of the video, in which we have learned very important concepts. One of the concepts learned here is that limit exists even if the function is not defined at that point. Perfect. Limit will only exist if left side limit is same as right side limit, as in this case. Here, since those two limits are not same, it does not exist. Perfect. For continuity of a function, we can at times define a function to plug in the hole If the limit of the function is same as the value of the function, then the function is continuous, otherwise the function is discontinuous. You will always find limit directly from a graph, sometimes from the equations. If you get a form 0 over 0, it is called indeterminate form. It indicates a common factor in numerator and denominator. We can find limit of such functions by techniques called factoring, rationalization, and substitution of variable. We have explored these techniques a bit here. You can always search for my videos Anil Kumar limits playlist to get into variety of examples and master this unit on limits. All the best. Thank you.